Hello. In this video, we're going to take a little look at vector notations as part of an introduction into two-dimensional motion, and then also other two or three-dimensional quantities that we may need in physics, things like forces, momentum, etc. So we'll start off by defining the difference between vector and scalar quantities. They are related to each other. They're both types of measurement, but vectors are mathematical quantities with both a magnitude and a direction. And as we've probably heard before, the term magnitude used, that refers to the size of a quantity. It's essentially what's the number, regardless of any sort of positive or negative sign on it. Doesn't matter if it's going up, down, left, or right. The size of a number is its magnitude. Sometimes also you can call it the absolute value if you're dealing with like a one-dimensional quantity, but vectors have size and direction. So a vector quantity could be something like displacement, because if I want to take an object and move it from one position to another, how far I go would be the magnitude of the displacement, but which direction I displace the object is very important. So if somebody says, go ahead and move this 3 feet, if that thing that you're trying to move 3 feet kind of matters which way you want it to go. Do you want it to go left, right, north, south, up, down? Which way do you want it to go? So vectors include direction. Other examples of vectors are velocity, acceleration, forces, momentum. All sorts of measurements we make in physics start out as vector quantities, and if we only look at the magnitude of it, then we're dealing with a scalar. Scalar is just essentially like a number on a scale. It's just there to denote the size of a measurement, but more specifically, scalar quantities are things that just don't have direction. So mass, the amount of stuff an object is made out of, we can measure that on a scale, but there's no direction attached to it. Time is also a scalar quantity. It's something we can measure, but there's no north or south for time, right? It's just it just counts on. So speed is a scalar while velocity is a vector. As we talked about before, speed only requires us to know the how fast something's going, not which direction it's going in. Now, in terms of working with scalars, those are easy. They're just numbers. You add, subtract, multiply, divide them. As long as you got the right type of units, you can do your regular arithmetic. But with vectors, we have to be careful because if we're not really sure which way they're pointing, as we have in the drawing down below here, if I have a vector that I'm going to label lowercase r, I'm going to put the little vector hat drawn on top of it. If I just told somebody that I had a vector of length 7, let's just say that that's what the length of that is, that would be a scalar quantity. But if this was a vector with a specific direction attached to it, I can't just add and subtract that from another number. I need to know which way they're pointing in. All the work that we do in physics in one-dimensional motion or even two-dimensional motion, we can only work in one dimension at a time. So we can't work in an X and a Y axis simultaneously if we don't know how much of the vector is going in the X direction, how much is going in the Y direction. So pictorially, having a picture like we have here helps us, but we also have 3 different notations that are very common for writing out how large a vector is. First up, which is more mathematical and not used as much in physics, is the bracket notation. So bracket notation takes the components of a vector in 2 different dimensions and puts them in what effectively is like an ordered pair to show you the position of an object. So an ordered pair in mathematics usually is using parentheses, and you have 1, 2 means you go 1 in the X direction, 2 in the Y direction, and that takes you to a point. Well, we can do the same thing here. If I want to say that on the x-axis, the distance from the origin to that point is rx, then that's my x component of the endpoint of my vector, but it's also going to be a position in space. And I can say right here is r sub y, the y component of my vector. And those do tell me the location of the end of the vector, but I have to draw the vector from the origin over. So that red arrow that I have represents a measured quantity in a specific direction. And we have the direction noted with the Greek letter theta there. So bracket notation is essentially doing an ordered pair, but you use the, what do you call them, like corner braces or greater than less than symbols here, pointy braces, to represent the fact that it's a vector, not a point in space that you're talking about. There's also polar form. Polar form would be written as just saying that the magnitude of the vector r is directed at an angle theta, and this angle theta is always going to be measured from the positive x-axis in a counterclockwise direction. So I'll say measure CCW counterclockwise from the positive x-axis. And that's just the traditional way of doing it in mathematics. So that vector, we could say it's rx comma ry to say where the vector ends up, or we could say it's magnitude r at angle theta. And you might recognize those, the magnitude bars there as absolute values, but absolute value just means the magnitude of a one-dimensional quantity. If you have a two-dimensional quantity, we'll discuss what is required in order to find the magnitude in a couple of minutes, but those bars mean magnitude of the vector. On the third way, which we're going to be very, very comfortable with eventually in this class, is component form. Component form it's kind of a longer version of bracket notation, but it's much more useful because we can separate one part of the vector, say the rx or the ry, and do our own mathematics with it without breaking apart the notation. We can just select this right here and say that that is the horizontal or x component of a vector, and the second part that we just add on to it is the y component. And we use the notation from mathematics of I, j, and k with a little arrow hat on it. And the arrow hat represents that it's a unit vector, but I represents the x direction, or along the x-axis. J represents the y-axis. And occasionally we'll use k to represent the z-axis if we're doing 3 dimensions, which isn't too often. But we can write something in this IJK notation, and it's a little bit easier to do mathematics with it later, which we'll practice with. But that's the 3 ways of making our vectors in various notations. Let's go ahead and practice that with the vector we have drawn here. I want to go ahead and show you how we can get into the 3 different notations. We've got bracket, polar, and component. And we're going to do that based upon what's drawn in the picture here. So for bracket notation, we're really just going to count across and see what the x value is and what the y value is. So that's 0, 0. We got 1, 2, 3, 4, 5, 6, 7, 8. So it looks like we're going to have 8 comma 1, 2, 3, 4, 5, 6. 8 comma 6. That's our vector r. So we could say that is equal to r with a little arrow hat on top of it. Now when I draw the arrow hat, and most people when they draw it, they only put the top part of the arrow, more like a barb. It's just because it's quicker. The computer will do the actual arrow, but for the most part, we just do the barb. Now let's go and take a look at polar form. In order to do polar form, we actually have to do a little calculation. We have to find the magnitude of the vector. So you're just going to use your good old distance formula that you used back in algebra in order to find that magnitude. And we're also going to figure out what the angle is. So we're going to do quite a bit of math for this. So how about we go and pause that and take a look at the component form, because the component form is really just the bracket form written out a little bit more lengthy. So we can say that the vector r is going to be 8i plus 6j. And we're done. That's it. Now you might think that seems kind of odd to write everything out like that when you got the bracket form, but it comes in handy later on when we're doing two-dimensional motion problems. Now, the polar form, we need to figure out what the magnitude of the vector r is, and we need to figure out what the angle of the vector is. So for magnitude, I'm going to take up a little bit of space over here, we would do this formula right here. The x component squared plus the y component squared, made an oops there, ry, and then square root them. So just the distance formula. If you want to find a distance from the origin to a point, that's what you would do. So in this case, we would have the magnitude is going to be 8 squared plus 6 squared, which is, of course, 64 plus 36, which is some number off the top of my head I don't know. So let's calculate up and see what we get. Don't know why I couldn't figure that out in my head. It's 10. It's magical 10. It's a 3, 4, 5 it's Pythagorean triple. How could I forget that? Okay. And the angle theta, well, we're going to use our trig. So we're going to do arctangent, or we could use any of the arc functions we want. But the arctan of opposite over adjacent. And for the angle that we've got there, our opposite side is 6 and our adjacent side is 8. So let's see what we get when we do that. We get 6, whoops. Oh my goodness, oh jeez. The lament. Click enter again there. No, wait, huh? Oh, there we go. These fake calculators are tricksy. All right, so 36.8, this is called 36.9. So for our component, we would, sorry, not our component form, for our polar form, we would say that this is 10 at an angle of 36.9. Now, if this was measured in meters or kilometers or whatever it is, whatever this vector happens to be, we could just add the unit onto the end of these right here. So we could put 8,6 and then meters on the outside of the bracket. We could put 8i plus 6j and then a parentheses and an m on the outside of it. But that's how we can do the 3 different forms. We're going to do a lot of component forms in our class, so get used to them.